Hello, friends. This is Mr. Shagney coming to you with lesson 13, which says that there are two graphs for every relationship. We've been studying proportions, and from proportions, we know that we can identify a constant or proportionality, also known as K. In identifying a constant proportionality, we also know that there exists two constants of proportionality for every proportional relationship. To find the second one, we know that we have to take the reciprocal. If we know that there are two constants of proportionality, then that means that there are two ways to visually represent them, which means that you should have two graphs for every proportional relationship. So that all makes sense. So now we're going to look at the first thing, which asks us to, beef up our math knowledge, and understand this sort of relationship in multiplicative patterns. So the first problem does just that. So I'm going to look at this problem and I'm going to evaluate it in kind of more than one way. I'm going to do it, the traditional way, and then I'm going to show you, using some patterns. But it only works in multiplicative equations, because remember, y equals kx. So for number one, I want to know if 3/2 of 16 is the same as 3 times 8. So I'm going to take 3/2 times 16 over 1. I'm going to first look to see if there's any relationships across from each other, and I see that I can divide 16 by 2 and I can divide 2 by 2. So I'm going to go ahead and do that. So this gives me 3 times 8, which is 24 over 1. And we should know that that just equals 24. Now, and then I look at the second part of the equation, which says 3 times 8, which is also 24. So those things do equal each other, so this one is true. Now, what you need to understand is that this is multiplication, so this only works in multiplication. So if you wanted to look at this in a different way, you could. So if I'm looking between these two factors here, 3/2 is half, or divided by, or if you look at it this way, if I'm looking at it this way, if I'm timesing this by 2, in a sense, like 1.5 times 2 gives me 3, and I'm dividing by 2 in this context, those are reciprocals, which means that they should be true, right? They're inverse relationships. So now I'm going to look at 2. Now 2 is different because I'm dividing, right? So when I divide the number, especially when I divide by a fraction, the number usually gets larger, especially if you start out with a large number like a whole and you're dividing by a smaller number, the number should be larger than both of your quantities. So I'm going to go ahead and use the same strategy. So I'm going to take 3/4, right, divided by 1/2. And remember, I'm going to use my keep, flip, change strategy here. So I'm going to take 3/4 times 2 over 1. I can again look to see if there's any relationship between the numbers. I see one. I can divide this by 2. I can divide this by 2. And so this is really 3 over 2. Which is, we all know, which is 1/2, right? 1.5. And then I'm going to do the second equation, which is 6/4 divided by 1/4. Now again, in this instance, I'm going to do, I'm going to take 6/4 times 4 over 1. I can go ahead and divide by 4 here, and this gives me 6. Now, this instance, right, these two are not the same, right, because when we divide by a fraction, this is more than a whole number. When we divided that whole number by a smaller part, it's going to, almost do something to our number. Now, these numbers do have a relationship, friends. 1.5 times 1.5 is 3, so I can only imagine that this goes in about 4 times. So it's really, what's happening is it's making the answer 4 times larger, and in this portion, even though that these technically were doubled, but division does that. So these are doubled in a sense. If you look at 3 to 6/4, that's doubled, and then this is cut in half, so it does have that, but it really doubled the answers, and so this is technically false. And again, this sort of understanding only happens in a multiplication instance. This is division, which is why that pattern doesn't work. I'm going to look at number 3. Number 3 is with decimals here, and so I'm going to take 13 times 2 8/10. So I'm going to do my, 13 times 2 8/10. 8 times 3 is 24. 8 times 1 is 8, plus 2 is 10. I'm going to then add a placeholder. Then I'm going to do 2 times 3, which is 6, and then 2 times 1, which is 2. And then I'm going to add, that's 4, 6, 3, and I have a 10th here, so I should at least have an answer to the 10th place. So that's 36 4/10. Then I'm going to take my second one, 52 times 7/10. So 7 times 4 is 14. 7 times 5 is 35, plus 1 is 36. And again, I have a number in the 10th place, so I should put a decimal in the 10th place. So 36 4/10 is the same, so this is true. Now again, this is a multiplicative relationship, like we're multiplying, right? So we can use our understanding of factors like we did in number 1 again here. Well, if I want to, I can look at 2 8/10 and 7/10. Well, I know 28 and 7 have a relationship, right? 7, 14, 21, 28. And I know that technically I would be dividing by 4 here. In the instance of the other number, so if I'm going from 13 to 52, well, I don't necessarily know if they have a relationship, but if I count by 13s, like 13, 26, 39, 52. So that's 4 times, right? 4 times larger. And 4 timesing by 4 and dividing by 4, those are reciprocals or inverse operations. And so that would make the equation true, but only in a multiplicative universe. So that is the first part of today's lesson. The second part of today's lesson, right, has us looking at tables, graphs, and equations. And so there's kind of a lot here, and we're gonna, take it as slow as we possibly can so that we can make sure that everyone's following along. So the first thing says that we can pick one of the following points to graph on the coordinate plane. Well, for this lesson, I'm going to pick the first one that I see, and I'm going to, it says on the graph, plot and label one of the points. Well, 10, 4. Remember, 10 goes first because it's x, and then I'm going to go up 4. So I'm going to be right about there, and then it says on the graph, plot and label. So I'm going to label 10, 4. Then it says use a ruler, there's an error there, to line up your point with the origin, 0, 0. Draw a line that starts at the origin, goes through your point, and continues to the edge of a graph. Now, I don't have a ruler here, but I'm just going to go ahead and do what it tells me to do in this instance, which just so that I want a point that goes kind of like that. Right, so that's part 2. And then part 3, for the people following along, is part 3 says complete the table with the coordinates of the points in the graph. Use a fraction to represent any value that is not a whole number. Well, I know that when x is 10, right, y is 4. And I know that because that's the point given. Now remember, to find the constant proportionality, we take y and we divide it by x. Now that's 4 divided by 10, also known as 4/10, right? We can read it like that. You can also know that it also can be written as a decimal, 4/10. Okay, so that now I know when x is 0. Well, what is y going to be? Well, that's 0. And then I know technically, when from this, when I divide it and got my constant proportionality, then I know that when it is 1, it's going to also be 4 out of 10 or 4/10. And if I take 4/10 divided by 1, I'm going to get the same thing, which is 4/10. So really, in reality, if you're following along, this is going to be a proportional relationship. So for this last column, you probably can go ahead and assume that it's all going to be 4/10 down this side, right? So from there, right, from there what we're going to do is, so if 1 is 4/10, then 2 would be double 4/10. So if I double 4/10, right, I'm timesing 4/10 by 2, right? So for all the people in here, I'm basically multiplying all these by 4/10. And multiplying by 4/10 is kind of like multiplying by the number 4. The only difference, right? The only difference in that is that it has a decimal point. So your answer is going to have to include that decimal point. So like 2 times 4 is 8. We should all know that, right? But because I multiply by a 10th, it's going to have a decimal point in the front, right? It needs to move one place. 3 times 4 is 12. But because there's a 10th, there should be a decimal point right in front of the 2. 4 times 4 is 16. And then we put a decimal point in between those. 5 times 4 is 20. And the decimal point, look at that. Like patterns, friends, patterns. 6 times 4 is 24. 7 times 4 is 28. 8 times 4 is 32. 9 times 4 is 36. And so it is, each one of these should have a decimal point because you're multiplying by a 10. So that says complete the table with coordinates and graph. Use a fraction representing any value that is not a whole number. Now number 4 says write an equation that represents the relationship between x and y defined by your point. Okay, so remember I told you that we're following, when we write an equation, x is always independent. So this right here is independent, which means that this is dependent. There are no labels here, right? And so I'm going to write in terms of y. So y equals, now from what we gathered, y, right? Y is going to equal the rate that we found at 1, right? So at 1, it is 4/10, right? Also found by dividing y by x on every single point. And then it's going to be times x, right? So that's a way to write one equation, right? And then the second, like if I wanted to say, hey, can you write an equation but going the opposite way? So x equals, right? If we change this up on you, so what's the reciprocal of 4/10, right? What's the reciprocal of 4/10? Well, if 1 is 4/10, then if I take 4/10 and flip it, doesn't that make that 10/4 y? Right? Like, doesn't that make sense if I flip this graph? And then, so those are your two equations, right? And then from there, we're going to compare, tables, equations, and graphs. So if we wanted to plot the other ones using just the points above, we're going to do that so that we can compare. We can compare each one so that you can kind of get a better sense of it. So if I plot it 4, 5, 4 is here, and then 5 is there. This represents point B. So this represents 4, 5. If I wanted to represent 8, 5, 8 and 5, 8 goes up to 5, right about there, and then I can draw a line there. So this is A, B, C, right? And I can label those so that everyone can see that. Now, if we're looking at all 3 of those lines, right, we've talked about a few things. If we wanted to compare them, well, I could say our graphs have different steepness, and steepness refers to slope, or has a higher constant of proportionality or a lower constant of proportionality in comparison to others. They're all proportional, right? You could say that. You could say that the equations, they all include a constant of proportionality. So in this, like, we can look at this and say that our graphs have different steepness. These graphs would have different steepness, or a different constant of proportionality. That's another way of saying that, right? Our equations, if we're looking at our equations, they would all have a COP. The COPs would be different for each one because they have a different steepness. Our tables would have different values, and those values would be different based off of the steepness of the graph, or just the constant proportionality itself. So what I'm trying to tell you all in the simplest way is that in this sort of example, right, from going from a table to a graph to an equation, I want to pull something out here. So this right here in a table is our constant of proportionality. We find that by taking y divided by x. And finding the constant of proportionality in a graph, right, you're given a point, right? You take y divided by x to find out what 1 is. So at 1, your dot's going to be right about there. We want to know when x is 1, what is y, right? And that's another way. What we've seen that as is 1 comma k. It's like, what is it? So when x is 1, what is the value of y? That also tells us our constant proportionality. And then the equation, right? The equation, when we write our equation, 4/10, right? That tells us our constant of proportionality. As long as it's in terms of y equals kx, right? It tells us all those things. So in looking at those three things, you should be able to pull out the constant of proportionality, whether I give you a table, a graph, or an equation. So that's the point of this activity, or point of this question, is so that you understand that. And if you're like, oh gosh, is he ever going to stop? No, that's the point of that. So looking at the next thing, so what is the y-coordinate of your graph when the x-coordinate is 1? Well, the y-coordinate is, so when x is 1, right, the y-coordinate, so remember, so when x is 1, what is our y-coordinate? Our y-coordinate is 4 out of 10. You can also write that as 1 and comma 4/10, right? That's for A. I'm still referring to A. I've done all the work for A. Plot and label this point on your graph. So we can go back to that. I'm going to plot. That's 1 comma 4/10. Right? Just following the directions. Where do you see this value in the table? Where do you see this in your equation? So in my table, right, if I take y divided by x, 10, if I see 4 divided by 10, that's where I find it in the table. In my equation, I see it again, see it here, right? 4/10 there. Describe any connections you see between the table. So my connection is, I can, the constant of proportionality. So the constant of proportionality is represented by y divided by x. That's in a table. It's represented by and an equation is represented by y equals kx. It's represented there in the equation. And in the graph, it's represented by 1 comma k, right? So I'm going to give you some seconds to write that down. So those are the ways that you represent the constant proportionality, right? You see that in a table as y divided by x. You see that in an equation as y equals k times x. And then you see that in a graph where it says the value of 1, right? The unit rate, you have k, the constant. So then it says the graph of an equation of the form y equals kx, where k is a positive number, is a line through 0, 0. Forgot those things. And the point 1 comma k. Name at least one line through 0, 0 that cannot be represented by an equation like this. So you're just thinking of a line that does not go through, that does go through 0, 0, but does not necessarily represent a proportional relationship. Well, I know 2 lines that go through 0, 0. They meet at a place called the origin, right? The line of x, right? So you have the x-axis and the y-axis. Both of those go through 0, 0. So you could say the x-axis and the y-axis. They go through 0, 0, but they do not have a proportional relationship because they're just increasing by increments of 1. And the second part says, if you could draw the graphs of all the equations of this form in the same coordinate plane, what would it look like? Well, basically, the first and third quadrants would be completely shaded in. So if you drew the x-axis and the y-axis, the first and third quadrants would be completely, shaded in. Give you some seconds to write that. So in that instance, right, in looking at that sort of relationship, it's not necessarily something that's important for now. It's just trying to extend our thinking a little bit further. And of course, the x and y-axis go through 0, 0, but are not represented by an equation. Right, that seems pretty self-explanatory to some degree. And then we have our last problem, right? It's the hot dog eating contest. So Andre and Jada were in a hot dog eating contest. Andre ate 10 hot dogs in 3 minutes. Jada ate 12 hot dogs in 5 minutes. Here are 2 different graphs that represent the situation. Notice that they're moving, right? So here this says number of hot dogs, which means that's our dependent variable in the situation, which means that time in this one is independent. And then in this one, time is independent and hot dogs are time is dependent and number of hot dogs are independent. I said that backwards and I apologize for that. So it says, on the first graph, which point shows Andre's consumption and which shows Jada's consumption? Well, Andre ate 10 hot dogs in 3 minutes. So he spent less time and he also ate less hot dogs. So if he ate less hot dogs, he should be lower. So I'm going to label this as Andre. So that means that this one would be Jada in this graph, right? And then in the second graph, Andre would have eaten less hot dogs and have the least amount of time. So this is also Andre here, which makes that Jada there. So that's what it's asked us to do in the first thing, is just label them. So then it says draw 2 lines, one through the origin and Andre's point and one through the origin and Jada's point. So this is just the first graph that they're talking about. I know that I'm going through both. So we're just going to now do the first graph and then we'll do the second graph in a second. I'm going to take this and try to make them, as perfect as I can. Right? So I drew the lines. One is Andre, the second one is Jada. Write an equation for each line. Use T to represent time in minutes and H to represent the number of hot dogs. So remember, in this instance, hot dogs are my dependent variables. So hot dog. So for Andre, hot dog equals. Now, using my information up there, because you're not given the graph, remember that if hot dogs are independent, so you take y divided by x. Well, in this case, y divided by x is 10 over 3, right? So 10 over 3, because this is hot dogs, and that's how many minutes he takes. 10/3, and then that's going to be t, because t is independent in that situation. For Jada, you're going to take hot dogs. Well, she ate 12 in 5 minutes, so I'm going to write 12/5 t. So for each equation, what does the constant proportionality tell you? Well, in each equation, in 1 minute, it tells you how many hot dogs each person consumed in 1 minute. So that's what I'm going to write. How many hot dogs are consumed in 1 minute? That's what it tells us. So how many hot dogs are consumed in 1 minute? And then so now we're going to go back to the second graph, right? So the second graph is going to be different. So they want us to, write a new equation, repeat the steps, draw a line, right? So I'm going to draw a line, and it's not going to be pretty. It's going to be, I'm going to try my best, right? And so this one, remember that time now is your dependent variable. So you're going to put these in terms of t. And like I said, in every situation, right, you have two constants of proportionality. We've identified the constant proportionality here, so really all I'm going to do now is I'm going to do the reciprocal, which this one would be for Andre 3/10 h. That means that he eats 1 hot dog and 3/10, right? 3/10, like 1 hot dog times 3/10 would be 3/10. So 3/10 minutes, right? 3/10, so 30 seconds, right? Like whatever that is time-wise. And then for Jada, she would have 5/12 h. So 1 hot dog, she eats in 5/12, right? So time. So if I took, 5/12 of a minute, if I took 3/10 of a minute, then you could figure that out. So that should make sense to some degree. I might have confused a little of you there, but really this is just a reciprocal because you have two graphs, so you should have it connects the idea that there are two constants of proportionality for proportional relationship, and then you should also have two ways of showing that. So this is what you need to do while I'm gone. The homework should be pretty straightforward. If you have any questions on it, you can save those questions for when I get back from my surgery. And then this is me letting you know that that is it.